right, welcome to this explainer review session where we're going to demystify amine chemistry and build you the ultimate high-yield study guide for your exams. If you've ever felt completely overwhelmed by organic chemistry pathways, or you found yourself tangled up trying to remember which reaction does exactly what, well, you are in the perfect place. Grab your notebooks because we're going to break this down piece by piece. By the end of this explainer, you're going to have a rock-solid mental map of amine reactivity. Let's dive in.
So, here's our roadmap for today. We'll be hitting 5 key areas. Meet the molecular blueprint, the basicity showdown, mastering synthesis pathways, identifying and reacting amines, and we'll wrap up with conquering aromatic amines.
Before we get into the heavy science, let's remember why we actually care about this stuff. From life-saving drugs like Novocaine to the literal adrenaline pumping through your veins right now, everything an amine does is dictated by one tiny thing: the nitrogen atom's lone pair of electrons. Think of that lone pair kind of like the steering wheel of a sports car. It's just one small component, right? But it entirely dictates the direction and the reactivity of the whole molecule, whether that's inside our biology or in massive industrial applications like making azo dyes.
Okay, part 1. Meet the molecular blueprint.
Think about the geometry for a second. We're looking at a physical compression from your standard tetrahedral angle, squeezed right down to 108 degrees. Why? Well, imagine 3 people sitting on a regular 4-person sofa, but the 4th invisible occupant, our lone pair, is sprawling out, taking up just a bit more space. It physically forces the 3 visible bonds closer together, giving us this distinct sp3 pyramidal shape.
You absolutely want to highlight this definition in your notes. Steric repulsion. It's literally the reason behind that compressed pyramidal shape. Your professors love to test this because it perfectly bridges physical physics with chemical geometry. It's a real classic exam concept. So the big takeaway here is that this single lone pair is pulling double duty. It acts as both a physical magnet for hydrogen bonding and a chemical engine, forcing the amine to behave dually as a Lewis base and a nucleophile. It's actively out there looking to donate those electrons. That explains why smaller amines are incredibly water-soluble. They use that lone pair to physically grab onto passing water molecules.
Moving right along to part 2, the basicity showdown.
Let's lay down the ground rules for how these amines fight for protons. Just remember, a lower pKb value means you've got a stronger base. In the gas phase, things are pretty straightforward. Alkyl groups push electron density onto nitrogen, making aliphatic primary amines the strongest bases compared to neutral ammonia and aromatic amines. We call this the inductive effect, or the plus I effect. It's just a fancy way of saying those surrounding carbon groups are basically cheering the nitrogen on, pushing more negative charge toward it. Aromatic amines, on the other hand, terribly weak bases. Their lone pair gets trapped running laps around the benzene ring in a process called resonance.
But drop them in water, and honestly, that whole logical order just completely breaks down. Suddenly, secondary amines hit this perfect Goldilocks zone. They have just enough electron push from the carbons, but not too much steric bulk blocking the stabilizing water molecules. Think about it. If you pack way too many bulky groups around the nitrogen, like you see in a tertiary amine, water physically cannot get in there to stabilize the cation. Secondary amines sit right in the sweet spot, achieving peak stability in aqueous solutions. Lock these summary basicity trends into your memory for your cheat sheet. Knowing exactly when to apply the gas phase inductive rule versus the aqueous solvation rule is a total game changer. And here's a pro tip. If your exam question doesn't explicitly specify a phase, always assume it's aqueous. This is exactly where they're going to try to trip you up on test day. I guarantee it.
All right, part 3, mastering synthesis pathways.
Now that we know the basic rules, let's open up the playbook and actually build these molecules. The secret to organic chemistry isn't just rote memorization, it's learning how to read the reaction pathways. Take the core pathways converging on the primary amine. There's a major trap to watch out for, though. Reacting alkyl halides directly with ammonia yields a really messy, difficult-to-separate mixture of primary, secondary, tertiary, and quaternary salts. Why? Because the newly formed primary amine is actually a much better nucleophile than the starting ammonia, so it just keeps reacting and reacting. Not great at all if you want a clean product.
Let's boil that complex network down to a simple mental checklist, making those dense flowcharts super manageable to memorize. Notice the second step, nitrile reduction? We call that a chain ascent because it actually adds a carbon to your chain. Keeping strict track of your carbon count is step number 1 for acing literally any synthesis question.
For the more specialized pathways, here's a little insider memory trick. Associate Hoffmann bromamide with chopping a carbon off, because it acts as a precise chain shortener. You start out with an amide, and the Hoffmann degradation violently removes the carbonyl carbon entirely. So if your exam asks you to go from a 4-carbon chain down to a 3-carbon amine, well, you know exactly which tool to pull from your kit.
Okay, massive exam trap alert right here. Put this in big red letters in your notes because it will show up on your test. Aryl halides totally resist nucleophilic substitution, which makes aromatic amines absolutely impossible to create via the Gabriel route. If you see a multiple-choice question asking how to synthesize aniline and Gabriel synthesis as an option, cross it out immediately. It is a trap.
Which brings us to part 4, identifying and reacting amines.
Let's mentally step into the lab for a second. How do you figure out exactly which amine is sitting in your flask? Think of the Hinsberg test as your 1-2-3 strikeout tool. It beautifully separates primary, secondary, and tertiary amines based entirely on their reaction to alkali. Primary amines form a product that dissolves in alkali because they still have a replaceable acidic hydrogen left over. Secondary amines react, sure, but they form an insoluble product because they're missing that extra acidic hydrogen. And tertiary amines? They strike out entirely. No reaction whatsoever.
Translating that complex diagnostic flow into a strict if X then Y logic checklist is an absolute lifesaver for lab practical exams. When you're standing at the bench stressed out and your solution goes clear the second you add alkali, you don't need to panic. You just check your mental logic table and instantly know, boom, you have a primary amine.
And finally, part 5, conquering aromatic amines.
So we've made it to the final boss battle of the review, the highly reactive, kind of wild world of aromatic amines. Before we even look at the mechanism, let's puzzle this out together. Why can't we just treat aniline like a simple benzene ring during nitration? I mean, it's just a benzene ring with an NH2 attached, right? What could possibly go wrong?
Well, the issue boils down to this. That NH2 group is so powerfully activating, it triggers wild, uncontrolled substitution. If you just dump bromine into a flask with aniline, it aggressively attacks every available position, giving you 2,4,6-tribromoaniline in a flash. And what if you try to nitrate it in strong acid? The acid protonates the amine, taking our powerful ortho-para-director and paradoxically turning it into a meta-director. It is pure chemical chaos.
The elegant workaround for this is the acylation protection strategy. It breaks down into 3 super simple steps. Protect the group, run the reaction safely, and then deprotect to get your clean product. Think of it like putting a temporary muzzle on an overly excited dog while you groom it. We react the amine with acetic anhydride, which temporarily distracts some of that lone pair's attention over towards a carbonyl group. Now the ring is calm enough to undergo normal substitution. Once we're finished, we just wash the muzzle off with water through hydrolysis, and we are left with a perfectly clean, para-substituted amine.
Once you've got that protection strategy down, you unlock diazonium salts. This is the ultimate synthetic gateway, allowing you to easily swap out nitrogen for halogens or create those brilliantly colored azo dyes. By treating an aromatic primary amine with nitrous acid at freezing temperatures, you create this wildly versatile intermediate. From there, you can use copper salts in the Sandmeyer reaction to attach a chlorine, bromine, or cyanide group, or you can couple it with phenols to create the heavily conjugated, super bright dyes that literally color the clothing industry today.
I want to leave you with this final thought. If something as unbelievably tiny as a single lone pair of electrons dictates so much chemistry, imagine the biological mysteries you can solve now that you actually hold the playbook. Understanding these fundamentals isn't just about passing your next organic chemistry exam, it's about seeing the hidden logic that literally runs our natural world. Keep these tools in your back pocket, rely on your flowcharts, and you are absolutely going to dominate your next test. Keep studying and stay curious.